Welcome back to real time digital signal processing lab. So, in the previous class we discussed about the speech coding. Today we will be seeing the demo of the linear predictive coding for speech synthesis. So, welcome back, and then we will see little bit of theory and then we will go for the demo both on MATLAB as well as in the board, actually, that is DSK board. So, first the introduction, because to give the feel of LPC what we discussed in the theory. This is linear predictive coding is widely used in speech coding, synthesis, speaker recognition and for speech storage. So, these methods provide extremely accurate estimates of speech parameters and does it efficiently. So, the basic idea here is to closely approximate the speech sample as a linear combination of past samples. So, as you can see in the equation, so what we have is S of n is the present sample. For that this thing k is going 1 to p, ak are the coefficients, S of n minus k. So, for some values of p, ak and then s will be predicting the thing. So, coming to the architecture for both analysis and synthesis of speech is what is shown in the figure here. So, we have the input speech, we can select depending on which speech we want to have the thing, and we have the digital filter, that is FIR filter. So, which is going to do the pre-emphasis on the thing, and this can be directly given as input to our moving average filter, which is shown as lattice moving average filter. So, one can go to the net and then check what is the moving average filter. So, as an input. So, the other way is what you are going to give to overlap analysis window, what it goes into the section. So, next is it is passed through the Hamming window. So, this is the FIR filter what we are going to design, and then we are going to check for the autocorrelation basically. So, we have discussed the correlation. So, here it is going to correlate with whether it is going to match with the present scenario, and it uses the Levinson-Durbin algorithm to predict the coefficients basically, and this is given as input to our lattice moving average filter. So, we are going to do time varying analysis basically over the fiber net what we can be connected. Here we will be doing both. Analysis is this equation and synthesis is this part. So, we will be incorporating both of it and then see the demo. Otherwise, in the normal case this will be becoming a channel and you will be sending it out, and then at the synthesis part, that is at the receiving part. So, we have to depredict the thing, that is we have to run the lattice filter, this which is a time varying moving average filter here. So, analysis receiver what it is going to have, and then the output is connected to our de-emphasis, and then output is going to be predicted. So, whatever input speech which is there, which should be coming out. So, what is the how it has been implemented, little details have been given here. So, first is because it is a speech which has to be segmented and taking the windows of it. So, the speech signal is divided into overlapping segments for further computation. So, the parameters used in this test scenario is window is the Hamming window, and window length chosen as 80 and window overlap is 40. So, as you can see, this is the speech signal which is a input signal, and we will be considering the overlapping window. So, you will be seeing that this is the window length and this is the hop length what it is called, and this is the overlap length. So, approximately you can take it as 50% of overlap what it has happened. As you can see here, it is given as 40. So, that is what the overlap length what will be taken, and these are the segments as you can see in this window length. So, we will be cutting the speech into smaller segments. So, and so on, and then till the end of the speech, and processing is going to happen. So, coming to the next is the autocorrelation. So, what we have to do it on this windowed signal, that is, this is done to minimize the expected value of squared error between the predicted signal and the true signal value. So, it is computed using equation. As you know, Rx is the autocorrelation coefficient of k is given by m is equal to minus infinity to infinity x of m into x of m minus k, and parameter for the autocorrelation function is the lag is taken as 9 in this case. So, next is the Levinson-Durbin algorithm for linear predictive coding, what we have to use the thing. So, the equations of the Levinson-Durbin recursion, basically it is a recursive algorithm which are used to compute the corresponding reflection coefficients and LPC parameters. So, the equations you will be seeing that given by A2 as you will be seeing up to E. So, this is your expected value of 0 which is given by phi of 0, and k I is calculated with this equation. So, for this thing is 1 less than or equal to I, which is less than or equal to P, okay. And then AI of I is given by this thing constant k I, and then after substituting in the equation. So, for j will be going between 1 to I minus 1, this is the recursion what we will be doing it. So, expected value of I is calculated with this equation, and then the updation alpha j is given by alpha j p between j between 1 and then p, that is the final solution what it is given. So, when it matches. So, the parameter is number of LPC coefficients chosen as 10 in this case. So, coming to the analysis filter, here it is FIR filter B is being used, uses the LPC coefficients as filter weights, and this filtering removes formants from speech signal, and the remaining signal after the subtraction of filtered modeled signal is called residue. So, what is it? Y of n is equal to A naught into A naught plus A 1. You may be wondering why A coefficients has been chosen. Usually we choose A coefficients for poles and then B coefficients for zeros basically. In this case you can see that A coefficients have been used for zeros. So, you will be having A naught plus, as you can see this is Y naught is A naught plus A 1 into x of n minus 1 is the input, plus A 2 into x of n minus 2 plus A 3 into x of n minus 3, and in time domain is expressed in this fashion, and in the z domain as you can see h of z is given by A naught plus A 1 into z minus 1 plus A 2 into z minus 2 plus A 3 into z minus 3, and filter length chosen is 10. So, you will be seeing x of n is the input, these are the coefficients, and then you are delaying the signal, and the other coefficients A 1 into x of n minus 1 or A 1 into z minus 1, what it is going to be coming from this leg basically, and you will be adding with your A naught, and then you will be getting the y of n. This is the filter structure what it shows, that how it is getting calculated. Now, in the synthesis part of it, it is the IR filter. So, now it must be triggering because the coefficients we have to keep the same A naught, A1, A2, A3. So, here it is IR filter, whereas in the analysis we use the FIR filter. Speech signal by reversing the analysis filter using the residue and LPC coefficients to recreate our formats. So, we will be using the all pole model of filter has the ability to describe most type of speech signals quite well. So, whatever zeros in the analysis part, now they become poles in the synthesis part, as you will be seeing it here. That is the reason why it was named as A coefficients. So, you will be seeing that impulse response h of z is given by y of z by x of z. So, which is given by some constant g divided by 1 minus k is equal to 1 to p or a k p into z minus k. So, y of n is given as if we write in the time domain, it is going to be g into z of n plus k is equal to 1 to p a k of p y of n minus k. So, these are the feedback path, and even here it is parameter, what is it, filter order is chosen as 10 equivalent to our analysis part. So, coming to this, the where all the LPC coding is going to be used, applications what you will be seeing it in the speech compression, example as GSM standard, and then speech encryption in the voice codec also. The example is electronic music, you can use the LPC coding, and tonal analysis of musical instruments you can use, and even in the speaker recognition. So, these are the references to create the files what it has been used. Okay. Now, we will first see the demo in the MATLAB and then go to the hardware to check the thing. So, first I will show you the LPC or this thing DSP, because this student has chosen as the project to implement it in the course. As I say, students will be taking as a mini project or they can use it as an assignment. So, what is it? Frame size, what it is chosen 40, as theory says frame length is 80 and LPC coefficient number is chosen as 10. So, what is this part is going to do? System object to read from an audio file and determine the file's audio sampling rate. So, when you are using it, you may not know the thing. So, what we will do is first we will read one of the file and then we will test it on the other two also. So, this is a Kannada. So, hold on what we are going to get through this. It is a M4 this thing format, student's own voice is recorded and then it is stored in the MP4 format. So, we will be taking input as we have to do the resample, whatever the sampling rate may be the thing. What we need is a 16 kilohertz. So, input with 16 kilohertz and then sampling frequency what we want to resample for 16 kilohertz. So, Fs is going to be defined with 16 kilohertz here, and then you will be starting and then some of the specific length of speech segment as 80, and then you have to do this zero padding to align on our this thing what is it length of it, and then you will be making some of the variables 0. So, you will be creating a buffer system object and set its properties such that you get an output of twice the length of the frame size with an overlap length of frame size. So, what you want to have is, although you are selecting 80 samples, 40 of them have to be overlapped. So, that is why you will be choosing the buffer length twice that of it, and then in that there will be 40 right side and 40 left side overlap will be there. So, this is the signal buffer what you are defining with twice that length. Next is each frame of input signal is windowed using a Hamming window. So, you will be calling DSP dot window which is given with Hamming window. So, the 10th order autocorrelation coefficients are found using this equations. So, you will be calling the function again DSP dot autocorrelator, and then what is the maximum lag source property, and then lag and LPC or coefficient -1, and then scaling and biased are the input to this. So, you will be this section what it does is calculates the reflection coefficients from the autocorrelation results using the LPC spectrum. So, you will be calling the Levinson solver to get the coefficients as you are doing it. So, then you will be creating an FIR digital filter used for our adaptive purpose. In the analysis case, also create two all pole digital filter system objects used for synthesis. So, you have to create the filters both for analysis and then synthesis. So, this is the analysis filter which is FIR filter which is declared, and then you will be seeing that it is a moving average lattice filter which is being used, and then you will be getting the coefficient here. And in the synthesis filter it is a all pole filter what you are designing it. You will be giving the structure and then a lattice all pole value basically. That is auto regression what you will be setting it. So, how you are going to play the thing? It is going to be written audio writer. So, you will be writing into the audio device writer. So, whatever the sample rate so which is selected as FS in this case. Okay. So, main code where LPC analysis and synthesis of the input audio signal using instantiations done whatever you have set it. Okay. So, the loop stops when we reach the end of the input file. So, which is detected by the audio file reader as a system object. So, you will be saying that frame size and then length of input -2 star frame size, and then taking input in segmentation you will be taking it, and then window each segment and then perform the autocorrelation here what you are doing it, then calculate the Levinson-Durbin algorithm in this place, and then synthesis filter is IR filter basically what it is being used, and then you will be writing in this thing, and then you can play output audio. So, writer what you are doing it, and you will be after everything you have to close the thing. So, you will be releasing the audio writer part of it. So, we will as I said this is the first file what has been taken for reading, and we will see the after synthesis analysis and synthesis what output you would be getting it. Okay. So, we will run the thing.
Namaskara.
Were you able to hear it? So, the selected one is telling Namaskara. So, we can see once again running it.
Namaskara.
Okay. So, what we will see is we will run the other part of it. So, we will open something what it has been stored wave file. So, we will run this.
Good evening.
Did you hear the thing? Again I will play it.
Good evening.
So, this is one more. So, you can, as I said, we can play with whatever your voice you want to have the thing. So, we will see this one.
Go away.
So, we can play the original and then see how it is going to look like.
Go away.
Okay. So, now what I will do is, this is from the MATLAB what we have played the thing. So, I can show you how it is going to be from the original wave file, whatever was it, and then what we were able to reconstruct. So, it takes a little time to play through the this thing.
Go away, 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 go away.
Okay. This was the original. So, what I will play here is from the this thing, what is it, analysis and then synthesis LPC coding, what we have done the thing. So, you would be seeing that there is a little difference with the original, just you will hear the thing again.
Go away.
But still it has a little meaning in the thing. So, as you know, LPC coding is 64 kilobits per second, what we are going to have it. So, the original voice in all the thing, what you can hear it from this place. Okay, I will play the other one, original.
Good evening, good evening, good evening, good evening, good evening, good evening, good.
So, as you can see, this is a female voice. Now, we have to take mean score of opinion, okay, here. So, what is it going to be? So, you will be hearing this good evening, how it is going to be, it has got reconstructed through our LPC coding.
Good evening. Good evening.
So, this is what you heard, okay. So, there is a difference between the voice, pitch and other things. So, you have to move on to the other standards and other things and see whether we are going to get the correctly, okay. That is what you have to do it, and then MATLAB.
Namaskara. 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 Namaskara.
This is the original voice.
Namaskara.
So, you will be seeing that after you have already heard, once again I am playing with the original and then the reconstructed.
Namaskara. Namaskara.
Still it was able to do the thing with some of the functions. So, you can recreate much more. So, before moving on to our demonstration in the Code Composer Studio, just I thought I will show you one of the application of our filter. So, here it is, usually we call it as multirate signal processing, which those who are interested can look into the thing. When I want to convert my CD quality, that is 44.1 kilohertz file to a MIDI quality, what we call it as 48 kilohertz. So, this is the input audio rate, and then output audio we want it at 48 kilohertz. So, how we are going to do it is going to be in stages, what we will be reconstructing. So, we will be having some filters in between when we are upsampling it, and then we will be using the FFT, that is audio, and then FFT what it will be coming, and then we will run and see this is one of the application of a filter. So, here it is going to happen in 3 stages basically. So, some of the filter you will be seeing it used here, it is for decimation and then interpolation, and then these are the 2 ones will be configuring to 2, the other one will be, last one will be this one. There will be 3 stages of it, and we will see that each stage how it is going to run with the thing. Okay. So, we will run this algorithm. So, and then see So, what happened? So, you will be seeing that if I make it maximize on the thing. So, you will be seeing here these are the 3 stages through the filter what it has got passed. Okay. So, from 44.1 what will be going to 48 kilohertz, which is depicted with respect to this. So, you will be seeing that initially the red one was at 44.1 kilohertz. Then based on our this thing both decimation and interpolation together we will be converting in 3 stages to 48 kilohertz. So, you will be seeing this is the black is the first stage, and then green is what it is going to be second stage, and this will be third stage what waveform it is going to look like. So, as you heard from the signal, this is a sine wave. Okay. There is no difference between your stages from one to the other one. So, without compromising on any input data, so we can reconstruct from one frequency to the other frequency. So, those who are interested, so this code will be up. So, you can look into the thing and then see that if you want to do from one why do you want to convert it into one frequency other frequency, because as we are seeing it our speech is at 8 kilohertz, and then from 8 kilohertz narrowband speech to wideband, if I want to convert it from 8 to 16 kilohertz what I have to convert. So, this requires multi-rate processing basically. So, those who are interested as a beyond this course material, you can go through and then get it. So, we will stop the MATLAB demo here. So, we will go into the Code Composer Studio and then check the demo of LPC coding. We will see how to proceed using the Code Composer Studio. So, this is the synthesis using LPC as it has been named, and then we need some include files, IO files and some math library, and then because we are going to use the codec in this case input and then output codec. So, we need this AAC 3106 init.h is our codec. So, we will be including the Hamming window as even in the FIR filter when I was demonstrating. Usually we create using the MATLAB and all our filter coefficients and then keep it. So, you can see here Hamming.h what I will open. So, this is the 80 order what it has been chosen, okay, Ham 80, and these are the coefficients in fixed point format what you have taken. So, fixed point format basically equivalent to what it represents in our board is integer format. So, you will be seeing 80 coefficients what it has been stored here, and which is used for our scamming window coefficients basically. This is the scaled version of it, and here also again the overlap is defined with 40 length, and then the frame length is defined with 80, that is twice that of it. So, you can include this thing speech samples what it is being stored, fine. So, initially I have taken Kannada 2.h and we have the other h file. So, we will see how does it look like, because you will be seeing that total length is 19,520. So, this is the total length of the speech samples what we have it, and this is how what it has got stored, okay, with respect to what I will say is in the fixed point format. So, you can see all of them are integers. So, the first one. So, after that what it is going to do? So, we have to define some data section. When we want to have in particular data place, we will define as hash pragma, that what we want this final output in the dot output. So, that is store the output in external memory, and we want the input to be also in the external memory. Then we will be putting it this way, because it is length input and output are more. So, the internal memory is less in the case. So, we want to store it in external memory, and you will be initializing basically. So, to show that print is to debug basically in between, if you are unable to get the output usually because this is a C code. So, in between to debug it, so you give print commands and then see whether it is matching with MATLAB. First usually all the codes are written in MATLAB and then tested that it is working, because we prove it there. Sometimes we have the built in functions in MATLAB for all these things. So, when we try it out and then it is working, then usually sometimes we may not use the built in function, we will write our own code, so that the code can be mapped into our Code Composer Studio or any hardware for that matter. Even if you are designing your thing in FPGA, usually in the MATLAB we test the thing. So, algorithm, or in using the Python code one can write their own algorithm, then we will be going into or transfer it to our whatever hardware which supports the languages. Usually in FPGA we use the Xilinx board, basically there we use both the VHDL as well as Verilog combinations to implement it. Even sometimes C will be front end and then back end will be VHDL coding, what we will be doing it. So, here also you will be seeing the front end in C. I will as I have promised one assembly program, I will show you that how the coding length is going to reduce, and then how you can predict what is the time it is going to take in later lab demonstration. So, this is the interrupt driven. So, usually here it is used as interrupt 4 actually, and then you are getting some input sample and then you want to put it in some dummy like dummy file, we say here dummy variable what it is going to be put, and then we will be taking it out. Okay. And if the index is less than the total, then you have to modify your input, and then you will be making it 0, because your window length is less and then your input length is more. So, you will be what I call it as circular buffer, what you will be putting it and then taking into that area. So, next is this is the segmentation function, input into frames of size whatever length it has been specified. So, from the start what it is going to do. So, you will be allocating some memory basically, and then you will be starting. So, you will be bifurcating your input wave, and then if you want to print it, that signal loop and other things what you can print it, so that it is entered into the loop. Okay. Then now comes the window function. So, this multiplies the segment with Hamming window. So, you are seeing that here it is doing the Hamming within the loop and then converting result from you can see Q format what it is shown. So, because the multiplication is going to result with Q30 format, so result has to be in the Q15 format. So, you are seeing that it is getting shifted by this thing 16 bits, and then here because we have two what we call it as sign bits, that is why one left shift is going to happen, and then later on 16 bits, and then we will be storing that in our this thing basically output, which is going to show that whether it is coming or not. Okay. So, then what it is going to, next one is your autocorrelation function, which is being implemented in C, as you can see. So, this is X correlation, what although it named as cross correlation. So, you will be using same data, so that it can be for two different data set input, or it can be the same input what you can provide. So, you will be initializing your correlation 0, and then you will be looping till your frame length minus I. So, that index does not spill over in this case. So, you are doing the basically what is it, only to the size of your data, and then you will be returning from this function. And then next is the LPC function, what it is defined here. It uses the Levinson-Durbin algorithm, and then it is going to calculate your LPC coefficients from autocorrelated segment, and you will be defining some of the variables and then allocating some memory here, and then what are the loop functions. You will be seeing that some of the k and e and then alpha, what it is being defined in the equation, which has to be incorporated, and then you will be iterating with this thing I is equal to 1 to odd as iteration is going to variable. Okay. So, you will be seeing that whether it has entered into this for debugging purposes, what you will be seeing in between printf statements. Now, this will be to the order you will be looping. This is the start step 1 here. So, you are calculating your sum and then k value and reference value, and then you will be calculating your modifying your alpha, and then you will be using it in your equation basically in the Levinson-Durbin equation, and you will be trying to minimize your error basically, and then E of I, and then you will be resetting your alpha value and other things, and then you will be freeing all your memory here. Okay. And this is the residual function, what it is being computed. Here FIR filter to calculate residual signal from windowed signal and LPC coefficients. Okay. Numerator size minus number of filter coefficients is equal to our number of LPC coefficients, what it is getting generated. So, this is the function what you will be writing it. So, then you will be summing it up, and then to check whether it is doing it correctly, you will be printing it. Then next, for the synthesis you have to run your IR filter. So, it is a all pull synthesize your speech from whatever you have done the analysis part of it, and then you will be reconstructing it. So, this is length here also IR filter length is 10 what it has been considered, and then you will do your equation, and then next is the buffering function. So, you want to accumulate because only for 80 samples what you are doing it, and then you are doing it in concatenation, that is there is a overlap and other things. So, you have to reconstruct your signal with a removal of overlap basically. So, you will be defragment and then put it in a concatenation using this function. So, finally, your all those are the functions which are defined, and then a main function what we will be seeing it here. Okay. So, all your outputs and then have been defined with 0, and then the loop what you will be giving it, that is iterates for every speech segment. Length here it is 80 and overlap what we have taken is 40, and every overlapping speech segment is going to be windowed. and do the autocorrelation later and calculate your LPC parameters and calculate the residual signal calculating using the FAR. So, you will be doing the synthesis through IAR and output the accumulation based on overlap. So, you will be seeing that these are the ones how you are going to free. And since we are using 3106 here L138, we have to initialize the interrupt service routine. So, we have to say what is the sampling rate we are providing it to the ADC. It is 16 kilohertz, even DAC is at the same thing, okay. And gains, what usually it is going to be 0 dB what we will be providing it, and then input to this is going to be from LCDK line input. So, even the output as here it supports both mic and then line input. Mic is we have a differential input, whereas line we will have both left channel and then right channel input what we can take it. So, that is how we will be working on one of the channel, or if you have two signals we can work on left and then right channel if it has been separately given, and then we will be looping back. So, now what we will do is, if you are doing it for the first time this code, it will take little time basically. So, since I have already compiled and then done the thing, directly I can go and then do the debugging part of it. So, you will be seeing that it has build has finished. So, the memory map what you are seeing it, how it is getting mapped into the board's memory, and then the code has to go and then load it onto the board. So, you will be seeing that the pointer you will be seeing in the C code. So, it has come to the main function where it is pointing to our program counter basically. So, it is now ready for the debugging is happened. So, I can cancel this memory map. So, you will be seeing, so that your debug is going to be seen. Okay. So, it has entered the main function here in the main. So, which is what we call in it's you can see the code both in C as well as mixed assembly. I will show you in a while, and this is where the entry point for the board basically C underscore int 00. This is the boot input, what entry point it has reached the thing, that is what it shows the thing. And then these are the what it says is we have used the EGDIS 110 USB debug cable for connecting it to the board. So, we will run and then you will be hearing the synthesized output from the board.
Namaskara. 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 Namaskara.
So, as you can hear that I am going to close my debugger as I did in the other example. Still the code is running on the board as you can hear it. So, unless I reset, it will be continuously running. So, I can disconnect from the debug. As you heard the thing, I can disconnect from my this thing system, and it can run directly as an input and output this thing system unit. So, we will see with other example how it is going to be depicted, that is input voice signal. Here I will take out from the this thing comment, and then I will comment the other one. So, it can be both in C and then C++. So, once I have done the modification, I had to do this is going to do debug and then say any errors are present. Since I do not have any errors in the thing, so what I will be doing is I can directly go into the debug mode. So, it will debug and then as you can see there are warnings, the section which was specified it says it has not taken the thing. So, some .h files have to be given. So, but still it is running. So, we sometimes if it does not run, some of the warnings you cannot ignore, you have to check with the thing.
Go away! Go away! Go away! Go away! Go away!
As you can see that it has become a male voice from the female voice. So, the last one we will see whether you would be able to hear from the board or not. I will be saving it and then I can debug. So, to give different this thing, we can create a gel file and from there we can provide different sections, so that while running itself I can modify it. Otherwise, I have to do debug and then rerun the thing. Okay. So,
Good evening. Good evening. Good evening. Good evening. Good evening.
so here it
Good
is
evening.
you are able to at least hear the female voice, but for the good one of the vo is almost getting I think swallowed or something, it is coming out as a good evening. Okay. We have seen the LPC speech coding basically both in MATLAB and then in Code Composer Studio using 6748 board. So, we will see other examples of scrambler, echo and equalizer in the using Code Composer Studio on the 6748 board in the next class. Thank you.